In our last class, we have discussed about voltage divider bias, and we have seen some of the many of the equations which will be coming across the bias scheme, and we have seen how to get to the output current and your voltages across your input and output bias circuit, and we have seen how to go through the different equations to find out the output current. Now we will see the concept wherein how the voltage divider bias is going to happen, and how the current and voltages will vary accordingly when the temperature increases or decreases. So that we will see now. Now we will see the voltage divider bias itself. Now, this is wherein we have seen the voltage divider bias in our last classes. So now, here I have used a silicon transistor having terminals, collector, base, emitter, and this is common emitter configuration. Okay. So now we have two resistors R1 and R2, which acts as what? Voltage divider bias resistors. And we have collector current limiting resistor RC, and we have RE, which is your emitter resistor, and this RE provides stable operating point. Okay, so because it has to, whatever your current is, that it has to pass through your RE, isn't it? So this provides this this RE resistor acts as what? Stability. It provides stability in your operating point. Okay. So now we will see. So what happens to the thing, or how the temperature variation will vary the current and voltages. So that we will see, and proper selection of resistors R1 and R2 is very important to have certain voltage drop across your R2 And what is that? What is this V2? V2 is what? It is the voltage across your R2, and this voltage acts as what? Bias voltage for your base to emitter junction. This is your input part of your transistor circuit, and VCE, the applied voltage VCC will be again dropped across your collector to emitter terminal, and remaining voltage will be dropped across your RC and RE resistors, and this VCE, voltage across your collector to emitter resistor, and this VCE is your output voltage drop or output bias voltage, or we can say it as. Okay, yes. So now we will see what happens. Okay, so now here, yes. So now what we have here is, so for example, if the temperature increases. Okay, so now we know that. Okay, for Ohm's law, what is the thing? So we have the Ohm's law, which is satisfying. Okay, or Ohm's law holds good only when we have the temperature which is not going to vary, isn't it? And also we know that as your temperature increases, semiconductors current flowing capability increases. For conductors, as temperature increases, current decreases, isn't it? So we know all these things. So now we will see on that basis how this is going to happen. Okay, so if your temperature increases, for example, if the temperature increases, so what happens here? As we have temperature increase, as temperature increases, what increases? What is the thing which is going to increase? What is that? As we have more, like this is our transistor, semiconductor device, as temperature increases, its current also increases, isn't it? So we have IC, the current which will be flowing through the device, and here we have IE and we have IB, your input current, isn't it? So what we can write here, the total current IE of your transistor can be written as what? IC plus IB, isn't it? So we know this. Okay, so as we know that your IB will be very small, so we have approximated IE will be equal to IC. So we can approximate this so and so, isn't it? Yes. So now your IE will be approximately equal to IC, and so we call your output current, or current to your transistor is said to be the collector current. Okay. Yes. So now what we can go through is, so as the temperature increases, IC also increases. Okay. Temperature increase. Okay. So as we have this temperature increase, IC increases. IC increases. When IC increases, what happens to the transistor circuit? So what happens here? As IC increases, what will increase again? So we have this IC increase. So we have notified that, we have said that, okay, the beta value of your transistor also increases, isn't it? So beta value, as the temperature increases, beta value. What is beta? It is the current gain in your common emitter configuration. Beta is said as what? IC divided by IB, isn't it? So beta is what? IC, output current divided by input current. Output current and IB is your input current. So beta value increases as the temperature increases. Beta value also increases. As beta value increases, in the sense IC value also like increases, isn't it? So IC, the output current obviously will increase. So IC increases. As IC increases, what will increase? What will increase? What will increase? IE. So we have said that IE is approximately equal to IC, isn't it? So as IC increases, the voltage drop across your RE, that will be, so in the sense IE increases. Okay, so not voltage drop. Okay, so voltage drop across your RE is said as what? VE. So now IE is the current which will be flowing through your RE, isn't it? Yes. So as IC increases, IE also increases. Fine. So as IC what happens? When IE increases, what happens here? What happens here? When IE increases, the voltage drop across your RE also increases. Isn't it? Isn't it or not? Okay, so we know that V is equal to I into R. Isn't it? As I increases, resistance will be constant. As I increases, V also increases. Isn't it? So we know that. So here, what we can say it as, so when I increases, voltage drop across your RE also increases. So VE increases. Isn't it? Isn't it or not? Okay. So VE increases. When VE increases, so what happens here in this loop? How we have written the thing last class? At this loop, if I apply KVL, what I can write this as? This is V2 will be equal to VBE plus VE. Isn't it? Okay. So V2 will be equal to VBE plus VE. We have written in our last class, isn't it? So if I apply KVL at this loop, so we will get this equation. So what we have seen here is, as we increase VE, so means whereas IC increases, IE increases in the sense. So what happens here is VE also increases. When VE increases, to make your V2 constant, what should decrease? VBE should decrease, isn't it? So VE increases, then VBE should decrease, isn't it or not? VBE should decrease and V2 will be kept constant, isn't it? So by this equation, we know that V2 is equal to VBE plus VE. So as VE increases due to temperature rise, because of all these things, so as VE increases, VBE should decrease, isn't it or not? Okay, so VBE should decrease. As VBE decreases, so then V2 will remain constant. As V2 remains constant, so what happens here? As V2 remains constant, the bias voltage is constant itself. Okay, so then IB will be same and IB will be what? IB will be same, and then the output current will come back to its original value. Isn't it? Isn't it or not? Okay, so this is how what we can say it as. Okay, isn't it or not? Right? Yes. So this is how we can say. So the total stability will be coming into picture, and this is how we have this operating point remaining at the constant value. Okay, isn't it or not? So we will see it once again. So what happens as temperature increases? So the output current. Okay, so the output current IC will increase. Okay, so because we have the semiconductor property which is said as the current carrying capability of your semiconductor will increase with temperature rise. Okay, so more and more electrons will be given out when we have this temperature which will be increasing. As temperature increases, more and more charge carriers will start moving, so that will make more current. Isn't it or not? Okay, so we know that, or because of your semiconductor property. For your conductors, what happens? So it is like a reverse, isn't it? So as temperature increases, current carrying capability of your conductor will decrease, isn't it? So temperature is a very important thing which will be influencing all your electronic circuits and components. Okay, so now we will see that. So as we have this temperature increase, IC will increase, the output current will increase. So this increase in your output current, okay, so this increase in your output current IC will do what? Okay, so as IC increases, what happens here? Okay, so as IC increases, VCE. So in the sense, so as IC increases, so what we have here is, so the output current IE will increase. Why? Because IE will increase. Why? Because as IC increases, IE should also increase, because here IE will be approximately equal to IC, and we have seen that. So as temperature increases, beta value increases in the sense the current gain increases. So that happens to the fact that increases. Okay, so after that, so we have that IE which is going to increase. So when IE increases, the voltage drop across your RE also increases. That is said as what? V2, isn't it? Final one. Okay, so as V2 increases, VE. Okay, so VE voltage drop across your RE, that is VE increases as IE increases. Okay, so then finally at this loop, if I say if I see at this loop, so we know that by KVL it is V2 will be equal to VBE plus VE. So we know that, isn't it? So what should be the thing? What should be the thing? So here as we can say it as VE increases, so this voltage, this VBE voltage should decrease. This VBE voltage should decrease in the sense, so as VBE voltage decreases, so what happens here is, so voltage decreases in the sense current also decreases, IB decreases. As IB decreases, so the IC which has increased before will decrease to the same proportion. So then IC again has decreased. So this is how it will bring the stability in your output current. So this is very important. Okay, so stability in your output current, in the sense stable output current is required. Okay, so temperature variation shouldn't make any of the current variation. Okay, so that is very important for any of the device. Okay, so any of the device and any of the circuit. Okay, so when we have this stable output current, your device is almost like it is performing the best. Okay, so this is how we will be taking, or we will be making the operating point to be stable with the use of what? RE, that is your emitter resistor RE. So RE is very important. Okay, on the basis of what it does is it makes your so all of the resistors will do, and this this is going to do the proper circuit. Like this will be the circuit component wherein your IB is going to come into a control value, isn't it? So this acts as what? Operating point control resistor. Okay, so this resistor will control the operating point properly. Okay, so this is wherein we have seen. So output current, that is IC, which is going to increase by the temperature. Again, that temperature increase will not affect the output current IC, because as IC increases, the circuit will make this IC to come back to the original value. Okay, so by the variation of all this voltage drop across different resistors, so the voltage drop reduce or increase will reduce or increase your current. Okay, so this is how the stability in your output current will be maintained. Okay, so this beta value is very important. Okay, so beta value will do what? Beta will be the so the current gain of your transistor. So this is very much important. Okay, so beta value is very important. So we have to remember this beta value. This beta is said as what? The current gain in your common emitter configuration. We have also seen alpha. Okay, in our last year classes. So what is alpha? So alpha is your current gain in your different configuration, isn't it? That is your common base configuration, isn't it? Yes. So this is how we can see all these things, and we will solve some of the problems in our next class on the basis of voltage divider bias. So this is all about today's class. Okay.